Every second, gigawatts of power flow across continental grids. 6G networks push terabytes of data through the air, and magnetic confinement fields hold star-like plasma inside nuclear fusion reactors. For most of human history, these exact same forces were a source of absolute terror. Early humans watched massive lightning strikes illuminate the sky, or stared at the natural pull of magnetic lodestones with absolutely no way to explain what was happening. The earliest natural philosophers faced a highly specific problem. They had to figure out how to capture, measure, and eventually predict forces they could not even see. Figuring out how to manipulate those invisible fields is what built the global power grid, modern telecommunications, and the internet. The first major breakthrough happened by accident in 1820. Danish physicist Hans Christian Ørsted noticed that an electrical current moving through a wire caused a nearby compass needle to physically deflect. Michael Faraday took that observation further. Though he lacked formal mathematical training, Faraday had brilliant spatial intuition. He visualized lines of force radiating from magnets and charges, physically filling the empty space between them to transmit energy. Then came James Clerk Maxwell. He translated Faraday's visual models into a rigorous mathematical architecture. Maxwell's equations proved that fluctuations in these fields travel as waves at roughly 300 million meters per second, proving that light itself is a wave of electromagnetism. By linking electricity and magnetism into a single calculable force, Maxwell provided the exact blueprint engineers still use to design everything from smartphone antennas to stealth aircraft. Writing down flawless physics on paper is very different from building it in the real world. When engineers try to scale equations into global infrastructure, thermodynamics and environmental realities push back hard. In 1858, engineers laid a transatlantic telegraph cable. When signals degraded, the chief electrician indiscriminately cranked up the voltage. This destroyed the cable's fragile insulation, failing to understand that the ocean and copper wire acted as a massive capacitor, storing and smearing the electrical pulses. William Thomson, later known as Lord Kelvin, realized the cable required precision, not raw power. He invented a highly sensitive mirror galvanometer to read faint signals and sent reverse electrical pulses down the line to artificially sharpen the transmission. Deploying this physics-driven solution required moving thousands of miles of heavy, properly insulated cable. It took the massive industrial capacity of the SS Great Eastern, one of the largest ships of its time, to carry the load in 1866. The transatlantic cable proved that complex systems operating in extreme environments fail when you rely on raw power. Scaling requires exact environmental modeling and predictive physics. Even perfect physics can fail if the economics don't make sense. At the turn of the 20th century, Nikola Tesla envisioned a world wireless system utilizing high-frequency alternating current. He built the massive Wardenclyffe tower to broadcast electrical power through the Earth and atmosphere. The fatal flaw was entirely commercial. Freely broadcast, uncontained wireless energy cannot be easily metered or controlled. Investors realized they couldn't monetize the power, and they starved the project of capital. Today, the main bottleneck for electromagnetic technology is rarely the mathematics. The primary constraint is the rigid thermodynamic limits of physical materials. We saw this clearly during the recent LK99 hype cycle. Social media went viral with claims of a room-temperature superconductor, but independent laboratories quickly proved the material was actually an insulator. A viral press release cannot bypass the strict laws of thermodynamics. A physical theory remains trapped in the lab until engineers find thermodynamically stable materials and highly viable economic use cases. To push past these limits, engineers are now using artificial intelligence to bypass the agonizingly slow human trial and error process of material discovery. Systems like DeepMind's GNoME AI analyze vast datasets to map hundreds of thousands of new atomic structures, hunting for the exact lattice configurations needed for next-generation magnetic materials. These AI-discovered materials are unlocking a field called Spintronics. Spintronics is a type of computing that uses the intrinsic quantum spin of electrons, rather than their physical charge, to process information. This allows massive AI chips to run with almost zero resistive heat loss. AI is also accelerating the discovery of high-temperature superconductors, or HTS. HTS are materials that conduct electricity with zero resistance at temperatures higher than absolute zero, allowing engineers to generate magnetic fields strong enough to make compact, commercial nuclear fusion a reality. By rapidly identifying the exact atomic structures we need, artificial intelligence is giving us the physical materials required to push Maxwell's classical equations to their absolute quantum limits. Yet this invisible architecture has one remaining, highly physical weakness: the global supply chains required to actually build it. The permanent magnets essential for electric vehicles and wind turbines rely entirely on the extraction of specific rare earth elements. Currently, over 90% of global rare earth production and processing is controlled by a single country, China, creating a fragile bottleneck for the clean energy transition. There is also an existential threat from space. Extreme solar storms, like a coronal mass ejection, can induce massive, damaging surges of direct current into our highly interdependent electrical grids, potentially destroying large transformer cores. We have mathematically mastered the invisible forces of the universe, but a technology is never truly finished until it can survive the brutal realities of manufacturing limits, geopolitical supply chains, and the physical environment.